This Wednesday, we're calling this a Flash Talk Social. I realize it's the AOS seminar, and thank you so much, Pete and Gerald, for hosting us. It was actually Tristan's idea that rather than have multiple Zoom meetings that people needed to do every week, why not combine these two? So thanks so much for hosting us. And it was also Tristan and Wayne's idea that we take a part of the globe, the Pacific region, and have presenters who are working on projects from that area present today. So to start, we're going to have Derrick Herndon from CIMSS, and probably most of you know that the Tropical Cyclone Group at CIMSS is renowned for the work that they do in satellite remote sensing. Millions of hits on the website daily. So with that, Derrick, I'll let you take it away. Thanks for presenting.
Thanks, Margaret, and welcome everyone. Yeah, it's been and obviously this year has been a very crazy, active year. We actually have our 10th hurricane of the season. Okay, can everyone see that?
Yes.
Okay, great, thank you. All right, so I am going to talk today about the CIMSS Tropical Cyclone Group's Pacific Hurricane Decision Support. And I just want to note, that the group is made up of me, Chris Veldon, Tim Olander, Tony Wimmers, Dave Stetner, Sarah Griffin, and congratulations to her and Kyle on their new baby. And Jason Dunyan and Jeff Hawkins act as remote collaborators. So when we think about hurricanes, we think about tropical cyclones, obviously living in the United States, a lot of the attention gets focused on the Atlantic storms because they tend to impact us the most and tend to get the most media coverage. But, tropical cyclones are global systems. And so we do want to develop products for other ocean basins. And at CIMSS, actually, this work started pretty early. Chris Veldon, one of his first papers, was on an intensity estimation algorithm to take data from a microwave instrument called the Microwave Sounding Unit and extract temperature information from that and produce estimates of intensity. And actually that work was expanded to the Western Pacific and developed in the Western Pacific. So a very early tool that actually was a Western Pacific focused tool to estimate the intensity of tropical cyclones out there. And not long after that, was the development of an infrared-based tool. So Tim Olander and Chris Veldon and others kind of worked on this. This is the objective Dvorak technique that was developed in the late 1990s. This is the original paper from 1998. And so it's around this time, really, that the CIMSS web page is really kind of getting going. And these products are starting to show up on the page. And actually, from a very, very early time, though these algorithms tended to be developed in the Atlantic, they were quickly transitioned to work in other ocean basins, including the Pacific, for reasons which I'll talk about in a second. And then in 1998, also, we had the launch of AMSUS, so kind of follow-on instrument to that MSU instrument, and further development of algorithms based on that instrument. And then we just kind of moved forward from there. And again, developed to use in all ocean basins at the time. As I mentioned, the Atlantic gets most of the attention here, and we do get quite a few storms, about 11 storms on average per year. So here's the IB-TRAX plot of storm density for the Atlantic. But the thing is that 85% of tropical cyclone activity actually occurs outside of the Atlantic. So far more activity occurs in the other ocean basins, especially the Western Pacific here. So on this density plot, you can see there's quite a bit more storm activity in the Western Pacific. And then also the Eastern Pacific as well, off of Mexico there. If you just look at some of the average numbers, the Northwest Pacific definitely by far has the most activity with an average of about 31 storms per year. But the Northeastern Pacific also pretty active at about 18 storms per year, and then also a few storms in the Central Pacific. So those are the storms that can sometimes impact Hawaii. It's not too common that Hawaii gets direct hits, but every couple of years they do get a storm that threatens them, and I'll talk about a particular case coming up. And then in the Southern Pacific, we also have some fairly active areas. American Samoa does get impacted by tropical cyclones. In that region, they get about 10 storms per year, and the South Pacific, Eastern Australia region. And then, of course, the Southern Indian Ocean takes up the bulk of the other Southern Hemisphere activity. So here's kind of a screenshot of our page for those of you who are not familiar with it. We display these tropical cyclone plots They are global, so when I did this screen grab, we had a tropical storm Epsilon, which is now a hurricane, but we also had 2 storms in the Western Pacific, one going into the South China Sea there, and then another system that was up to the north and west of Guam. And our users, use these products daily for tropical cyclone work. Even when there are no storms, they'll use the products down below, so the imagery and derived products from that satellite imagery, such as winds and moisture and things like that, just to look for areas of possible genesis. And then off to the left, I just kind of have a listing of some of the agencies that we support. So the National Hurricane Center, the Central Pacific Hurricane Center, the Joint Typhoon Warning Center. Those 3 agencies kind of make up the bulk of the people who use our products. And then we also have Kadena Air Force Base out in Okinawa, American Samoa, Fiji, the Bureau of Meteorology in Australia, Central Weather Bureau in Taiwan, National Weather Service out in Guam, Japanese Meteorological Agency, Korean Meteorological Agency in Indonesia. And just kind of make a note down here that, obviously weather is 24 hours occurrence, 24/7. And though we can't promise we'll be there 24/7 to fix things, if something goes awry, we do what we can to help our customers, even if it's an evening or a weekend, because we know how important these products are. And in some cases, some of these products are some of the only products that these agencies have access to. In terms of the kind of guidance that we're providing here, we're providing information on the tropical cyclone environment. So what is the wind shear doing? How is it progressing and changing? Storm steering flow, moisture, trends in the vorticity. And then we have tropical cyclone intensity algorithms, some of which I mentioned, the advanced Dvorak technique, the microwave sounders, the satellite consensus, which is kind of a blend of all those estimates, the Archer, which is really more about position, but does have intensity information as well. And then really a focus on forecasting right now is trying to observe and forecast tropical cyclone structure. So for that, we have the Archer. The sounders can provide information on the thermal structure of the storm. Is it becoming extratropical? Is it a subtropical system or a purely tropical system? And then, of course, the geostationary infrared, visible, and water vapor imagery can also provide information on structure. And then finally, tropical cyclone position. So automated algorithms such as the Archer algorithm, and then subjective interpretation of the imagery from the microwave and geostationary channels. And so here's kind of just showing the current storm in the South China Sea, a plot of the wind shear, and here's just kind of a representation of the Archer of that plots for that storm, showing the automated position tracks of the storm going across the Philippines. I wanted to just kind of show a little bit about how this might play out in some of these regions. So this is a case for Major Hurricane Lane, which was making an approach to Hawaii. So the Central Pacific Hurricane Center takes over the warnings for this system once it crosses 140 west. And here's a plot of the GFS ensemble plots and tracks for Hurricane Lane. At the time, the system was a major hurricane at 105 knots, but was expected to intensify and then turn to the north potentially and actually make landfall in Hawaii as a hurricane, which is somewhat rare, but it does occur. And when it does, it's very substantial, especially in terms of flooding. But you can see there's quite a bit of uncertainty in these plots here, and the forecast going forward is quite uncertain, primarily because of wind shear. So this is one of the plots that they were looking at from the Central Pacific Hurricane Center when they were analyzing Lane. And at the time, Lane is located in an area of these green plots here, these green lines indicating low wind shear, but there's much higher wind shear out ahead of Lane. And so the concern was that the storm would encounter this wind shear and that would impact the intensity, but it would also impact the track of the storm. And so that's highlighted here in their Central Pacific Hurricane discussion from August 20th, where they're saying, the models are showing that this year is going to increase and will impact the circulation, but how much it's going to impact the storm is a bit uncertain, and this is creating problems for the forecast going forward. So these tools can be used both in an analysis framework, but also to look at the environment ahead of the storm, and that can help them to determine how the storm will be impacted and the forecast going forward. And this animation didn't show up, so I'll exit here and I'll go to the browser just to show kind of how Lane evolved. And so this is a radar representation of the storm as it was approaching Hawaii from Brian McNulty's page. And we can see the circulation here in the southern part now coming into view, and we see the eye is fairly well formed with an eye wall. And one of the tools we've developed actually is an eye wall replacement tool that will allow forecasters to determine when a storm will undergo an eye wall replacement cycle. And we can actually see that structure evolving with the storm with a secondary eye wall. But what happens is that as the storm begins to move towards Hawaii, that shear that I talked about basically separates the mid-level circulation, which moves off to the northeast, and then the low-level circulation is left to move off to the west. And the storm actually never really made a real landfall, even though it did produce rainfall over the Hawaiian Islands. So that's a really good representation of how the wind shear product can be used in the forecast to determine a potential forecast impact. And the agencies do use these products all the time. So then here's a plot of how the storm actually tracks. See that track to the west-northwest, that turn that was forecast. But again, those representations in the model that showed a turn to the west because of the higher wind shear is what ended up verifying. Another major user of our products is the Joint Typhoon Warning Center out in Hawaii. And I'm just showing this to show, you know, when you think about the Hurricane Center's area of responsibility, the Atlantic and the Eastern Pacific, the Central Pacific Hurricanes area of responsibility, the Joint Typhoon Warning Center has responsibility for everything else on this map here. They're not an official RSMC, which are plotted on here, but they have responsibility for a large area of the ocean basins here. And so they need a lot of assistance in putting their forecast together and doing their analysis. And it's not uncommon for them to be dealing with multiple storms in multiple basins at the same time. So here is a plot of 4 storms that were going on, 3 storms in the southern hemisphere, 1 storm in the northern hemisphere. And so one of the things that we can do is these products that we have that are automated can allow the forecasters to kind of quickly move through the analysis part. So the intensity analysis, the structure analysis, and the position analysis makes their jobs a little faster, and that allows them to spend more time on the forecast. And that's really, really key when they have multiple storms that they're dealing with. As I showed in that plot earlier, there's a lot more activity in these other ocean basins. And I just want to highlight the fact that the Joint Typhoon Warning Center is producing these products for the military, and everything that the military does is impacted by the weather or the ocean environment in some way. And tropical cyclones obviously are high impact events and potentially costly. So some of the bases that they are responsible for are plotted here. I mentioned Guam, so there's National Weather Service Guam, but there's also the Andersen Air Force Base, Kwajalein, Kadena Air Force Base, U.S. Forces Japan, and Korea. And so this is just kind of a microcosm of the areas that they're responsible for. There are a lot of military assets that they're responsible for in this region, and so they need all the assistance they can in helping put the forecast together. So as a result, one of the things that we did do is we put together a dedicated web page for them. So the Joint Typhoon Warning Center made a request. They said, hey, we get a lot of storms out here. We need help understanding genesis of storms. And so we developed a specific page for them that basically produces plots of storms a little bit earlier than they would be produced on our main page, because they want to get a quick handle on how those storms are evolving and set the conditions of readiness for the various bases that they're responsible for. I want to talk about another case, and this was interesting. Tony Wimmers brought this up in a talk that he did earlier this week, and this isn't the specific impact that he was talking about, but I wanted to talk a little bit about American Samoa. So we have an agency out there that does forecasts, but they don't have necessarily all the tools available to them. So in this case, there actually is no radar for these islands to track tropical cyclones. So one of the tools that they can use is the MIMIC product, the animation of the microwave imagery in the 89 gigahertz range, which produces radar-like presentations of the storm. And so they can use this as kind of a proxy for radar to track storms across the islands and see how they're evolving. So in terms of the intensity, but also really importantly in terms of the rainfall impacts. And on the rainfall front, this was another case for American Samoa. So this is the total precipitable water product. And again, without any access to radar in terms of forecasting how much rain is going to occur, this is a very key product that they can use to determine the amount of moisture. So in this case, we had a monsoon trough set up over American Samoa that was feeding moisture over the islands. And then on top of that, there was also a tropical cyclone Gita, that was approaching the island. So this system produced a lot of damage, but it also produced tremendous flooding for that region. And they were able to use these products in order to help in the forecast. In terms of training efforts, we have a number of different workshops and conferences that we attend to kind of bring this information out into the Pacific. So one of them is the International Workshop on Satellite Analysis, the IWSAT-C. So that was held in 2011 and 2016, and we had several attendees from the Pacific regions. And so this gives us an opportunity to go out there. Typically, this is held in Hawaii, but it might move around. But updating the community on the latest advances in the tropical cyclone analysis tools, genesis, and satellite tools that we're developing. And then the International Workshop on Tropical Cyclones is also held every 4 years, so we attend those. Again, those are broadly attended by folks from the Pacific region. In addition to that, we might do site visits to the various operations centers to do training, or they may send representatives to SSEC for training. And that also allows them to come to us and say, look, these are the areas of focus for research that we're interested in, and then we can help develop tools to assist them with that. And then also the Tropical Cyclone Conference, which is the military tropical cyclone conference. Again, the primary goal there is that TC impacts on military installations and operations, and especially for the U.S. Pacific Command area of responsibility. So with that, I think I'll stop here, and I might have a minute or so for a question. We'll see.
Thanks, Derrick. Yeah, we have time for questions. You guys can either raise your hand through Blackboard Collaborate or write a question in the chat. Well, Derrick, I have a question. Are you the main person behind the Dvorak technique? I don't know if I'm pronouncing that right.
Yeah, no, Tim Olander is the one who spearheads that. Yeah.
Well, it's so popular.
I work primarily,
on social media.
yeah, I work primarily with the microwave sounder methods and the satellite consensus, which uses the ADT as a member.
Thanks. Well, I don't see anything in the chat or any hands up. So let's move on to the next speaker. And we have Mike Foster from SSEC, and his title is along the lines of supporting Himawari 8 within the Taiwan CWB. So Mike, can you share your screen?
Yes, hopefully. Can everyone hear me? Or can anyone hear me?
Yes. Yep.
Okay. There we go.
Yeah, I can see a screen.
You can see it?
Got it. Yep.
How's it look? Okay. Okay, so thanks, Margaret. So yeah, I wanted to just talk a little bit about a collaborative project between CIMSS and the Central Weather Bureau of Taiwan. This project started in 2016, and basically the primary goal is to use the expertise at CIMSS to help CWB develop some decision support product forecast center. In particular, it's a pretty good fit because there's lots of products and algorithms that were developed here for the GOES-R satellites that were trained or validated against the Himawari 8, and that's the satellite that Taiwan is using, launched by Japan. And so a secondary goal of this project is to have somebody from CWB come and visit CIMSS for 3 months each year. And so we've been doing that. We did that 3 years. It has really worked out well for us and for them. It's been a really nice part of the project. This year we did not do it for obvious reasons, but hopefully we can do it again next year. So I work mostly with cloud remote sensing. So I work a lot in the ClaverX products. So for those who don't know, ClaverX is a processing system developed by Andy Heidinger's team, and within that system, we've developed a lot of the operational cloud retrieval algorithms for NOAA, for the JPSS and the GOES-R programs. So in particular, the cloud mask, cloud optical property retrievals, and the cloud height algorithms were developed in ClaverX. So the first thing we did for that CWB collaboration is run ClaverX, so they had access to some of the basic cloud properties, and those have now made their way into some of the operational daily weather reports, I guess, for the CWB. And then other than that, there's been a lot of different projects that have gone on. I've listed a few of them here, and I've grouped them into the ClaverX versus the non-ClaverX products. And I really just want to say this has been a really nice project, and that it's been truly a collaboration, and that dozens of people from CIMSS have contributed So I have not tried to name them all because if I did, I knew I would forget some. But the point is that there's a lot of really interesting work, and I've had the opportunity to meet people I hadn't met before and to learn more about products that I did not know that much about. So in that sense, it has been a success. And in the last couple minutes or few minutes, I just want to go over two particular products that we're working on right now that have recently had some pretty interesting results, and that's the QPE and the near surface visibility. So the first one is the quantitative precipitation estimate, specifically derived from cloud microphysical properties. So this is not the NOAA operational algorithm. This is something a little different, taking advantage of CLAVRX and the cloud properties. And this is work that Tim Wagner has been leading. So this is based on Roebling-Holman paper from 2011, where they're developing a rain rate based on cloud properties, specifically cloud water path and rain column height. And the equations are here, but basically the gist of it is you can come up with some thresholds for cloud water path, which is CWP 0 here, above which you could expect precipitating clouds to exist, and then you can estimate what that rain rate is going to be based on the column height and cloud water path. So the trick is to find thresholds that work. So our first year, which was last year, we worked on this, and we took that Holman methodology and we tried to retrain using radar data over Taiwan. And what we found was we had a very difficult time finding thresholds that were physical. And the reason for this, we believe, was because there are a lot of very intense precipitation events that occur in that area of the world that do not occur where the original algorithm was trained, which was Northern Europe. And so at the end of the year, we had retrained the algorithm to work over Taiwan. We got okay results, but we were not overjoyed with them. So this year, Tim decided to wade into the machine learning toolbox. And again, we're still relying on the cloud properties. You can see here, this is just a heat map, which is just sort of saying the red areas are saying two input parameters are correlated, the blue saying they're anti-correlated. And the RRS all the way in the bottom right-hand corner is the rain rate. And the idea here is that we've just got a bunch of different input parameters. We're going to feed them into a machine learning tool and see if we can come up with a pretty good model for predicting when we have rain and when we don't have rain. And for this, Tim chose the random undersampling boosted decision tree. You know, you can ask him. I know a little bit about it, but you can ask him if you have specific questions. So we trained using instantaneous rain rate data from the radar that we got from CWB. We had Taiwan is a very mountainous region, so there was some beam blockage thing, and so we had to do some quality assurance. Originally, our results were not that great. Tim settled on this red box of data, and we got a month of data. In fact, I think now we're getting more because we wanted to get a better distribution of precipitating and non-precipitating cases. And this is a area under curve. This is the results we got. Actually, this is the results we got originally with NextRad data, but they're similar with the Taiwan data. And area under curve is, if the short way to say this is, if this is 1, if you're doing a perfect job, this graph would look like a square. So we're doing a really good job. 0.96 is a really good value for this. And this is what the current rain mask looks like using that RUS boosted model. The left is the radar data. The center is the Himawari model based on the cloud products and the IR bands. And then the right is the 0.65 reflectance, just so you can see what it looks like. So that was a success story. However, part of this is that we split this QPE product into 2 parts. One is to create a rain mask, and the other is to create and estimate the intensity. And so we are currently working on the intensity, and that is proving to be pretty big problem. So again, there's a lot of very intense precipitation events that occur in this part of the world, and we are finding it very difficult to predict those, in part because I think our cloud properties are saturating, our optical depth is saturating too quickly for us to have a lot of information to be able to differentiate heavy versus very heavy precipitation events. So I will leave that there. Have a little bit more time here. So the other one I wanted to talk about quickly was the near surface visibility. And this is work that Coda Phillips is doing. This started with a fog mask product that the CWB has been working on. And so they wanted to work with us to take that product and use our cloud properties, our cloud optical depth and height, to come up with an estimate of visibility, near surface visibility. And so to train that product, we got a whole bunch of weather station data that was measuring visibility across Taiwan. And unfortunately, what happened was when we started to dig in and really look at this data, it turned out there was a great deal of variability among how visibility was reported among the different sites. It was very inconsistent. So sometimes it was measured by an observer, sometimes an instrument, sometimes they would have a lot of measurements in a short period of time, and sometimes they would have very few. They would have different maximum visibilities at some stations, and it was just very difficult. So what Coda did was he decided that he was going to make the problem a little bit easier, and instead of predicting an exact visibility amount, instead we would look at what the probability of the visibility being below 8 kilometers was. That wasn't a completely random choice to 8 kilometers. It was based on the VFR, visibility flight rules threshold, which is something used for aviation. And then basically he was, again, going to use some machine learning tools. This time it was a random forest classifier, and he was feeding in the relative humidity, the ceiling of the cloud base, whether or not there was present precipitation occurring, and aerosol optical depth. Sorry, I'm losing my voice a little bit here. And that ended up being a much more manageable problem. So this is for under the random forest classifier, the figure you see in the bottom left. On the bottom you have the predicted, and on the left you have the true. And the idea is that the yellow is saying the upper left-hand corner is when it's getting above that threshold, high visibility. The bottom right-hand corner is when it's below that threshold, low visibility. And we're getting it right about 80% of the time. The other nice thing is in the upper right-hand corner, we can see our output probability is pretty good, is in line with our true value probability, or true value of threshold. And then the bottom right-hand corner is really just to say that, for example, that very purple line is the 100% visibility is low, meaning we know that visibility is low, and that is occurring, that distribution is occurring far to the left, which is what we would hope. And basically we're just looking for sort of a smooth transition as we decrease the peak probability of the visibility being below 8 kilometers, and that is what we are seeing. And then applying this to the weather station data, we can look here, and Coda said, okay, if we have 10 kilometers and we take each 10 percentile of that probability and multiply it by 10 and subtract it, you can sort of have an estimate of what your visibility might look like between 0 and 10 kilometers. And we have two stations here, and the first thing that probably pops out is that one of them has a maximum visibility of 20 kilometers, and one of them has a maximum visibility of 10 kilometers with, for some strange reason, an occasional jump up to like 18 or 19 kilometers. These are the kind of the reasons why we really couldn't have a consistent visibility estimate amongst all the different stations. But what you can see is that that orange line, which is the predicted model, is capturing a lot of the variability that the actual station is measuring. And so that if you wanted to, you could have some kind of a factor to try to match up the predicted with the actual, but it's not clear to us how we would, it's not clear the physical reason for doing that, but it's something we're exploring. And that's it. That's where I'm ending. So if anybody has any questions. Thank you.
Thanks, Mike. Okay, Angela has a question that she put in the chat box about the QPE product. Given the challenges in developing the product, do you have a sense of how good of an accuracy would be considered at least a moderate success when compared to ground-based estimates?
I guess I would say it depends on if you're looking for a rain mask or a rain rate. We got some really nice, I'm pretty confident that our rain mask, we're getting some good performance. I mean, I wouldn't, this is not meant to, you know, replace radar or anything like that, but maybe to supplement it in areas where radar is not available. The intensity, we still have work to do. I would say we're not where we need to be in terms of estimating the rain intensity. I don't know if that helps.
Yeah, I think I wanted to mention anyone can unmute themselves also. So Brad has a question. So Brad, why don't you unmute yourself and ask it, please?
Yeah, Mike, the visibility work was interesting. I'm wondering whether you've looked, there was an option 2 visibility retrieval developed for GOES-R that used aerosol optical depth and then a number of meteorology parameters to estimate visibility. That's available in IMAP. I'm wondering whether you've tested that against using the MORE aerosol optical depth retrieval as the input.
So I looked at the ATBD, this is way back when, that you wrote, I think, or you were part of that team, correct?
Yep.
I did not know that is that a product that is actually available currently?
So it was an option 2. It didn't go into operations, but, and Kathy can interject here, I think it's available through IMAP or CSPP.
Okay, yeah, I did not
Kathy's
know that.
great.
If we can get a hold of that, that would be great.
Yeah, you know, it kind of dead-ended with funding, but it was using, you know, it uses GFS MET parameters along with aerosol optical depth to do a prediction, estimate of the visibility, and if you applied that as a threshold like you are, you might get better results as well. We tried to do it as a more than just a one threshold. I think Kathy, but it is available.
Yeah, I mean, we started trying to do just an actual estimate of the number, and it's a tough problem. So
Yep.
this is something we are exploring now. It's still being useful and maybe more consistent over the varying stations that we're dealing with. But yeah.
So this is Kathy. This is Kathy, Mike, and it still is part of IMAP. We're producing it from our direct broadcast every day. It was integrated as part of, it was one of the GeoCap products. So I'm very happy to talk to you more about it if you'd like.
Yeah, that would be great. Okay. All right.
Okay, well, that was a great discussion. I hope that Mike, super interesting presentation, and thanks everyone for chiming in. Next up, Angela Rowe from the AOS department is going to present on radar-based studies of extreme rainfall in Taiwan. Thanks, Angela.
Thanks. Can you hear me okay?
Yep. And I can see your
Great.
screen.
And
We can see it.
perfect. So that was a good transition because there was mention of a challenge in this area is because of just how intense the rainfall is. And that's why I'm so interested in this region, is to better understand extreme and heavy rainfall, particularly in the region of Taiwan. So for those who may not be as familiar with the geography of the region, there is a large mountain range north-south oriented. So the central mountain range is a north-south oriented here, and then you've got the snow mountain range that extends up to the northeast. So this plays a large role in modifying the location and intensity of heavy rainfall throughout the island, which has dire consequences. So there's a lot of flooding that can occur in very densely populated. So here's an example from 2017 in the Taipei Basin with extreme flooding that has a lot of implications for the areas in this region. And this heavy rainfall comes from a lot of different types of phenomenon. So the most obvious one in this region is our typhoons. So here's an example of a pretty extreme scenario of Typhoon Morakot in 2009. Here's a radar snapshot from that period. And what I particularly want to point out, so the center moves more towards the north end of Taiwan, but it's this rain band here oriented west, east, interacting with the central mountain range here in this location. So it's absolutely catastrophic rainfall and consequences. So just to talk about how heavy and extreme the rainfall is in this region, the 4-day total was nearly 3,000 millimeters, and this was a large chunk of the annual rainfall that had occurred in this region. So this scale doesn't even really do justice for just how much rain had fallen in this region, but you can see it's concentrated here along the western slopes of the central mountain range. And this had a particularly heavy impact on the region and was one of the things that really has gotten my attention for caring a lot about this region, was visiting the site of this village that had been entirely wiped out by a landslide from this extreme rainfall. So this is a really extreme example, but one that's been largely studied with very important implications that are related to the topography of this region. But in addition to typhoons, which we'll see more in the later part of summer and early fall, late spring and early summer is the Meiyu season. So the Meiyu front, is what it's referred to in Taiwan, is a shallow front that meanders north and south throughout this time of year, late spring and into summer. And here's an example from that June 2017 case with a flooding in Taipei City, where you can see the heavy rainfall and the embedded regions of heavy rainfall along this front that's then modified as it moves further south over the terrain. But at the same time, there's also southwesterly flow bringing in moist air to the region that's interacting with the topography and creating persistent rainfall over the southern half of the country as well. And here's another example of heavy rainfall, in this case from the Meiyu and southwesterly flow, where the areas of heavy rainfall were concentrated in northern Taiwan near Taipei Basin, as well as certain locations across the mountains. And for example, we had, there was measured 635 millimeters in 12 hours. So this is what we're meaning by heavy rainfall in the Taiwan region. So there's been projects for decades over Taiwan to try to study heavy rainfall. So back in the 90s, there was a project TAMX looking at Meiyu season over northern Taiwan. And my first involvement in Taiwan was as a graduate student participating in TIMREX, which was focused on southern Taiwan in 2008. And here's just a very basic overview, very radar-centric overview of this project, where the NCAR S-Polka radar located on the southwest coast here. So we had a good view of both the ocean, focusing on that southwesterly monsoon flow, as well as looking towards the western slopes of the Central Mountain Range towards the northeast. There were also, the operational radars from the Central Weather Bureau, as well as additional research radars from Taiwan that were at times co-located and other times moved about this general region. So here's a picture of the SPOLCA radar. It's a dual polarization Doppler dual frequency radar. The dual frequency aspect is helpful for looking at humidity with the radar, but the dual pole aspect was the particular draw and what I've been most interested in and was part of my dissertation back then. And here's just some example of the type of information we could get from the data, because the radar is able to do these vertical cross sections, or these RHIs. So here's one that's looking particularly towards the Central Mountain. And this a May front type of event, but an afternoon thunderstorm case where you had persistent echo forming along the slopes. You can see here this, the outflow is intersecting some of the southwesterly flow and leading to continued regeneration of convection over this region along the western slopes. And the dual polarization tools here gives us an estimate of the dominant hydrometeor type that suggests there is some ice hydrometeors on the order of Grapple that can be seen at least aloft near the topography. So this was a big focus of my research, and what I was interested in was the role of terrain and how these systems, both these afternoon type systems and those that move onshore, embedded within the front, are impacted by the topography. So the main conclusion from TIMREX, there's a lot of relationships that were discovered and published related to wind shear, boundary layer processes, particularly the cold pool and microphysics associated with these convection systems. And oh, I hear an echo. Okay, we're good. That I could give a whole seminar on, but we learned a lot about convection in this region in the southwest part of Taiwan. And in particular, you know, looking at these embedded systems in the Mayu that move onshore, interact with the terrain, where I saw this upslope tilt, an increased role of ice-based processes over the slopes. And so these large ice hydrometeors can be present, can play more of a role as we get towards the slope in creating some of these heavy rainfall. And we're trying to think about this in the context of the different dominant microphysical processes leading to heavy precipitation, compared to whether we've got these more isolated convective systems versus the wider stratiform with embedded convective regions moving in along the front. So that was quite a while ago, and since then there's been a lot of research on this. Taiwan has an incredibly impressive operational network in terms of rain gauges and radars and regular soundings. And for about the past 5 years, we've been involved in discussions with researchers in Taiwan about what does the next heavy rain project look like in Taiwan, and how do we broaden this collaboration even further to think about not just Taiwan, but the West Pacific as a whole. So from this, the PRECIP project was born, the Prediction of Rainfall Extremes Companion in the Pacific. It was supposed to be PRECIP 2020, where we were going to coordinate with Taiwan, and their equivalent project is called TAHOPE. You can see our designs of our logos here. The Japanese component was TPARC, and that was going to be a primarily an aircraft component, but also focusing on some ground-based measurements, which I'll talk about shortly. We also had a NOAA component where we were going to have the P3 focusing primarily on the typhoon part of this. But the idea, you can see the duration of this project, is we would cover the Mayu season, afternoon thunderstorms in the summer, and then going into typhoon season to get a wide spectrum of types of heavy rain producing systems that would culminate with the Olympics that were going to be in Japan. And the idea here is this process-based focus where the field experiment really is thinking about the processes contributing to rainfall from a wide range of phenomena, from the Mayu to the typhoons, and then afternoon thunderstorms in between. And this involves not only these measurements, but there's also a significant modeling component, including many different cloud resolving models, different ensembles, and really an effort to improve the predictability. You see that's the first word in PRECIP here. We really wanted to better understand the predictability of rainfall using this area that experiences very heavy, frequently heavy rainfall as a wonderful natural laboratory to address these issues. So my group in particular is a collaboration. So the PRECIP project on the NSF side is led by Michael Bell at CSU. And then there's many subgroups within us, some focusing more on observation, some more on the data simulation or prediction side of things. So my group is really interested in collaboration with Kristen Rasmussen at CSU and Allison Nugent at University of Hawaii on the orographic influence on the heavy rainfall. And we're taking project-wide a very ingredient-based approach where the precipitation is related to the rainfall and duration. And we think about kind of this classic Dawes-One model, thinking about measuring the different ingredients and understanding which are the most important in these different rain scenarios. So we want to quantify those individual ingredients from the observations to distinguish their magnitudes between heavy and non-heavy rain events, try to determine common and unique mesoscale, microscale processes that lead to the heavy rain, and then in particular, as I mentioned, use observations and a model component to understand the terrain interactions and how they modify these ingredients. And we use this framework where we think about, again, precipitation in the spectrum of rainfall intensity versus duration, and you get increasingly extreme rainfall that can be short duration, high intensity, where strong vertical forcing is hypothesized to be more important, whereas the strong horizontal forcing and the more large-scale transport of moisture may be more relevant for these long duration events where, for example, we have broad regions of stratiform, where tropical cyclones is kind of on the upper end of the spectrum. So this is the framework in which we've designed this project in terms of observations, models, and our science questions, with our group focusing on the topography. So the observational approach, particularly the radar, we are again implementing the NCAR as POCA radar. And this time, instead of Southwest Taiwan, we're putting it farther to the north. And there's many reasons for this, but one in particular is there's a small island. It's the southernmost in the Japan chain of islands, Yonaguni Islands, where they have already put a few smaller cloud radars. And we also will be putting the CSU C-band. It was recently designed for shipborne deployments, and it's now going to be put on the island here. And the idea is we get this cross-section across the mountains. There'll be an additional mobile radar put here on the east coast, northeast coast, to fill in the low gaps on the east side of Taiwan. And basically, we're coordinating our scans over the course of these 3 months to be able to get statistics, and then also allow for some user-defined periods for certain events, depending on, for example, if it's the Mayu or a typhoon coming through. But the idea is we get these long-term in the sense of these types of projects where we get actually 3 months of radar data looking across the central mountain range in this region. So you can see some of the simulated results that we had for this kind of setup where we can really nicely see these systems as they move on around the topography from either direction. And defining heavy rain is a big part of this. So for Taiwan, what they call heavy rain is going to be different from what we may in other locations. So we'll start with these CWB definitions, where you think about these 24-hour or hourly accumulations, but then modify these more on the spectrum so that this could be more broadly applicable to other locations as we think about this ingredients-based approach. So I won't go into this in more detail, but there are these very specific categories, at least for warnings in the Taiwan area, where by the time you get to this extremely torrential rainfall, you can see now we're thinking in these 24-hour time periods. So obviously it is a really big disappointment about everything that's happened this year, not being able to move forward with this project. But as with anything in science, you take this as an opportunity. So we're not sitting idly by. The one unfortunate aspect of this is because we have to move it to next year, we won't have the NOAA P3 available. But we will have additional instrumentation that wasn't going to be available this year from the Japan end, for example, and also introducing potentially micropulse style LiDARs to get moisture variability across this information. So there can be a silver lining. So this summer, I've been looking at revisiting the CIMSS data to try to quantify some of the things we saw now in this heavy rain framework. So can we distinguish these characteristics from such a short-term data set as we collected during TIMREX? And the answer is sort of, but it gives kind of a framework for what we can build off of for these longer-term data sets from the radar as POCA going forward into PRECIP. And this was the big event that we did this summer. So it was an opportunity to do a pilot study or a really extensive dry run for the whole summer. So we coordinated with Taiwan for daily weather briefings from the Central Weather Bureau for the first couple weeks of June. And in this case, we were able to not only use all of their ensemble model forecasts, but from the US side, we had MPES running and the Penn State ensemble that assimilated Himawari data to be able to get a look at some of the variation and the predictability for these events for this summer. There's also the operational data that we're using, the radars, the soundings, to try to start looking at some of the model biases and also some of the processes, because we did have a mixture of heavy rain events this summer that we could look at. Although it was kind of an unusual year where the front, you can see it here, there's Taiwan, the front actually stayed quite north a lot of the year, a lot of the season, producing very heavy rainfall over Japan. So again, maybe it was a blessing in disguise, and we'll have a more normal year next year. Although even with this unusual circumstance, there was still a ton of rain. So I'm going to stop there. I just wanted to kind of introduce you to the research we're doing there and what we have in store, and fingers crossed that things move forward in 2021. Thank you.
Thanks, Angela. I think of all the things I've heard of that's been derailed from COVID, this is one of the big ones. Brad, go ahead and ask your question.
So Angela, that's very, very interesting. So it's probably just because I'm naive about that area, but it's the first time I've heard about this combination of both convective and orographic precipitation. Is that unique to these places, islands in the tropics, or is orography also intensifying the convection? And could you say a little more about that combination of orographic lifting and convection?
Yeah, so what I'm referring to there is twofold. One is just in terms of the afternoon convection, the initiation and the focal point of where things can initiate. But mostly, yeah, we're taking this ingredient-based approach of how are you enhancing the ingredients leading to some of the convection. And in this case that I showed, for example, in TIMREX, is you have that more localized uplift that can contribute to larger hydrometeors as it kind of tilts upslope in that location. So we want to think about its influence, say, on vertical velocity at that convective scale as one example. That's not unique to this area per se, and that's kind of the point, as we can see how this is more broadly applicable to the regions. For example, I compared what we saw in TIMREX to what we saw in Northwest Mexico during the North American monsoon season as one example. So the idea is if stripping down to this ingredients-based approach, can we think about things more fundamentally to apply to other regions? I hope that answered your question.
Yeah. Thank you.
Yeah, thanks, Angela. Okay, we should move on to our last presenter, Scott Lindstrom. Scott came to the AOSS building in 1982 for grad school, and he currently makes training material for the NWS and satellite blogs. His title is Time Series of Satellite and Satellite-derived Information Created for Pacific Region. I think he might have a shorter title now, but thanks, Scott.
Yeah, this is my title now. I hope you can hear me. My internet is not always very good, but this is work that Alexa and I have done. And you can see our pictures there in case you've forgotten what we look like in the last, 8 months or so. So there is a history of CIMSS support to the Pacific region. OCONUS, Jordan Girth, who's now in the National Weather Service Office of Observations, was the JPSS satellite liaison for a long time for OCONUS, so that's Pacific region, Alaska region, and Puerto Rico. The goal is to increase satellite use. CIMSS manages a lot of direct broadcast antennas through the Pacific region, and CSPP software is used to process the data. So there is this CIMSS relationship to a lot of agencies that are working in the Pacific region. So the first thing that I want to talk about is something that kind of grew out of a request that I got from Paul Stoy, he wanted those 16 data at one point, a time series of it for a couple months, multi-channels. And I thought, well, I figured the Geo2Grid, which was created here, could do this. So I, of course, asked Dave Hayes to make a little Python script for me, which is on the screen here. So I created these, for Paul's story, these time series of channels 1, 2, and 3 from Go16. And then I was thinking, well, you know, I do some work for training for the Weather Service office. The National Weather Service has a single office in the Southern Hemisphere in Pongo Pongo, American Samoa. And I thought, well, wouldn't it be useful for them to have information about Go17? So I told Alexa about this project that I did for Paul and said, can you do this for Go17 at just one point? So that's just what I'm going to be talking about today. So we have a year of band 13 Go17 data. And this is because forecasters in Pongo are really only using satellite data. Mike mentioned that there's no, someone mentioned that there's no radar there. That was the case. So they can only use satellite information, and they really only use geostationary satellites. So there's a real need for training there and for information. I thought, well, I'll just give them these, you know, this information about what's normal for a year in Pongo. And similarly, the people in the Pacific region headquarters said, you know, they've created total precipitable water climatologies from the soundings that they take in Pongo. So can you create that from Mimic TPW too as well? So I did that as well. And I'm also preparing some training for Pongo in late November, early December. So here we have a box and whisker plot. I never remember what a box and whisker plot means, so I put it, well, Alexa helped me to put a key here on. So the red line, of course, is the median. They're quartile bounds on the top and the bottom of the blue box. And then we have some outliers that are shown. There are a lot of outliers. So the outliers are more than 1.5 times the quartile range away from the bottom or the top. So you see there's a lot more outliers on the cold side than on the warm side. So this is for Honolulu. We did this for 4 stations. If anybody wants a annual time series plot every half hour for 4 different stations in the Pacific, do some time series analysis just to figure out how to do that, just send me an email. So this is for Honolulu. Here's the one for Pongo. And in case you don't know where American Samoa is, there's a little map inset here. I like American Samoa because I always imagined that some huge bird just fell on top of the island, and you see the beak of the bird here, where Pongo Pongo is, and we have the wings spreading out. And the Weather Service office is over here. So this is just showing you how does the brightness temperature Go17 vary over the course of the year. And you see you are more likely to have very cold cloud tops associated with convection. I think it's interesting here that February has the coldest temperatures. That, of course, is the beginning of the southern hemisphere. So that's in the beginning of that's the middle of their summer, I think. We also have Alexa also made some plots. I just wanted to mention this is hourly data. I want to do it more frequently than that, but Go17 had the mode 3 to mode 6 switch. It went from 15-minute imagery to 10-minute imagery. I guess, you know, in 2020 you could do this every 10 minutes if you wanted to. We also have things for Anchorage and for Seattle that are shown here. So you just get kind of a feel for band 13. How does, you know, what's the growth? How do the brightness temperatures change over the course of the year? So just to give them information back in Pongo to say, you know, if you see this kind of brightness temperature on top of you in March, or if it's a very warm temperature, how normal is that? Just gives them some bounds of climatology. It's just 1 year of data, so you don't really know how it's going to change with time. But it's something that can be, it's some things that can baseline their observations. I mentioned I did this with total precipitable water comparisons as well. So this is looking at CIMSS values for 4 years, and then it's comparing it to values from the observations from the soundings that are taken at the airport in Pongo. So it's also been done for those 16 locations. I did this for San Juan. I'm not going to show it to you, but Puerto Rico is also Oconus outside of the continental United States. In Madison and Kansas City and Boston, it's just some nifty little software that Alexa has created. It makes a time series plot at one point for an individual satellite channel from the geostationary satellite. I thought that was kind of an interesting thing. So if you have questions, comments, those are our email addresses. So that's all I have. Just a quick little review of what we do for the National Weather Service on Pongo.
Thanks, Scott. Any questions? We're a little bit over, but or you can email Scott or Alexa. Well, once again, AOS, thanks for hosting us this week. And take care, everyone. Thanks.
Thank you.